Okay, looks good. It's up to you. Sure, you can always do this if you want to show it. It's up to them. Yeah. I'm just prioritizing what's happening here, and as long as the good thing is I've taken charge of the sound and the video here. I'm self-contained, and that's all that matters. Yes. And if they want to, they should just do it like a pure math talk. That was what I told them. So, yeah, and the stuff on the slides, that will be still visible from the camera will track. If I point to the camera will track, and then they'll get it through the camera. That's how I was thinking. Oh yeah, sure. Okay, well that's up to. Okay. There will be other sounds but I'll just have to lean close. Okay. But the speaker. Yeah, but I'll be making instruments and stuff. So let's just. Yeah. Well,
and if something doesn't work,
yeah.
we are monitoring.
Yes. Okay. All right.
If something happens.
Just. Madid or Madid?
Madid.
Okay, did. Okay. All right. Yeah, sure. What?
Your mic is
yeah,
working, like
sure. Okay, well, I'll keep talking. Should probably start, right? It's 5 after. Yeah. Yeah.
All right, so. Welcome everyone. Bienvenue à tous. Donc la dernière exposé de cette semaine de conférence distinguée en mathématiques appliquées. Merci beaucoup. So welcome everyone to this last installment of our week of distinguished lectures in applied mathematics for this year at least. It is a great pleasure to have again Alex Barnett from Flatiron Institute to give today's lecture, colloquium in fact. Alex got his PhD from Harvard in physics some time ago. He then went to Mass General to do radiology, to study radiology, and after some time moved to Courant Institute and to do more numerics and numerical analysis related things. After which Alex was hired at Dartmouth and did part of his academic career there, going up the ladder and to the rank of professor until 2017, at which point he was, I don't know, it's a bit of a diffuse, we need to talk about this, but went to Pattern Institute is one of these institutes that is probably a little gem, you know, should be considered a little gem in North America where you can actually do research and all the way with a slanting, producing software and maintaining it, and it's in New York City. So today, without further ado, let's thank Alex for a talk on the mathematics of sound and music. Welcome, Alex.
Thank you. Thanks, JC. I'm going to move this closer to the instruments and things here. It's great to be here, to be back. I've been to Montreal several times for various spectral geometry workshops over the years, and I gave a research talk here on Tuesday, and also the other speaker, Nilima Nigam, I'm delighted to be sharing sort of this week's applied math talks with her, and because a lot of our research overlaps, and including what I'm going to talk about today. So let me and do a lot on the chalkboard. So I'm probably going to want to pay most attention over to this side. So yes, so I'm a musician as well as a mathematician. So that's just music is just a spare time activity. But I taught a class at Dartmouth on music and sound for non-math majors. So this is going to be some of the sort of highlights of the math connections in music and sound. So what is sound? Well, amazingly, you might recall that we all live under a huge column of air pressing on us. And it's actually pressing really hard, right? 1 atmosphere of air pressing on us is roughly 1 kilogram force on every square centimeter. That's a lot, right? If you think how small a square centimeter is and how quite large a kilogram of force is. And you may remember that the weather changes, especially now, right? You're noticing it. The atmospheric pressure varies by about plus or minus 5%. And this usually happens over days. This is the sort of time scale that the air pressure changes around us when we talk about weather. But there's some other things going on with pressure in the vicinity of your head. And so let's take a pressure measuring device, and in this case it's called my laptop, and let's run a piece of software, which you should all have and play around with. It's called Audacity. You should get it if you don't have it. And what this lets you do is measure pressure, amazingly. So does someone want to come up? I'm going to volunteer to you. Do you want to come up and make a sound? Any sound you like. Yeah. Okay. Can you make a longer one or something, maybe using your mouth? Very nice. Thank you. Perfect. Thank you. Okay, so what's going on here? Let's get rid of the second graph. Just focus on one of these graphs. Okay, so we're going to zoom in on that graph. So I'm going to zoom in repeatedly, stretching out the x-axis, which represents time. So zooming in more and more. You can see there's a lot of chaos going on right there. You can see it's going up and down so much. We're starting to see something. Okay, something is changing almost in a repeating pattern, right? And have a look at the timescales it's changing on. So here's 13.23 seconds. This is 235. Okay, this is 13.24 seconds. So the gap between maybe this pulse here and this one is about 100th of a second. Right? So what we're seeing here is a graph of pressure versus time. So P, and well, you might remember that there's this huge pressure from the atmosphere already. So this one's going up and down about 0. So what this is doing is telling you the change relative to the current atmospheric pressure. Right? So really this P here, we should call pressure, right? This is pressure relative to 1 atmosphere, whatever the current atmospheric pressure is, and T is time, and something's happening, but the time scale in which that's happening is roughly 100th of a second, maybe 1,000th of a second. In fact, you can zoom in, you can keep zooming in, and eventually you start to see the individual samples in the computer, and they're separated down on the scale of like a 10,000th of a second. So nothing much is happening below there. It's almost impossible to see what's going on the 1 second time scale. Okay, so that's kind of the time scales that sound shows up on, right? So this is and what we're going to do, the math of this is that this is a function, P of T. It just records how much what the pressure deviation from its resting value is as a function of time. So one of the other questions would be, we know the horizontal scale, what's the vertical scale? Does anyone want to guess? What kind of pressure variations is this laptop microphone measuring? Relative to an atmosphere, let's say.
Sound wave.
Sound waves, yes, but I'm asking for an actual number. Like, is it 1,000th of an atmosphere change, relative change? Anyone want to guess? 10 to the minus 2, so that would be 100th of an atmosphere. Okay, well you would have lost your hearing, probably, if it were that loud. Okay, so it's actually a lot smaller. A millionth, yeah, it's about a millionth. So actually, this here is really, so in math we'd write 10 to the minus 6 atmospheres, and this one would be minus 10 to the minus 6 atmospheres. So, right, so 10 to the minus 6 means 1 over a million. Again, I'm not going to assume very much math knowledge in this, right? These are very small changes, right? Our ear can actually, we can detect even better than this. We can detect 10 to the minus 10. Now I know you've got the system of 10 to the minus something. You can detect pressure changes at 10 to the minus 10 atmospheres, and that's down at the threshold of human hearing. So how does that get to you? So I don't really have time to go into waves and everything, because Nilima did a great job of dealing with waves, but I'm going to give you an idea of how that gets to you. So who wants to hold the end of this? Actually, it'd be good if you do. All right. Okay, so this is a model for how sound is transmitted and but in the air. Now, we're in tension. We're both pulling. The air is actually pushing. It's in compression. But other than that, you can imagine each little piece is a piece of air. And then how does a pressure change that I produce get to your ear? Well, it goes like this. Right? So do you feel it? You can see his hand shaking. So that's what happens to the microphone or an ear. It literally gets shaked by the fact that I'm pushing, and the push goes down in what's called a longitudinal wave in the air. And it doesn't go sideways like that, although that's more fun to look at. But that's a transverse wave, and sound doesn't do that. It just pushes. So another way I could generate a compressional or longitudinal wave is by taking a pocket, compressing it, and then exploding it, like that. Right? So okay, so that's basically how sound's transmitted. That's a thing called the wave equation, the one-dimensional wave equation in this case, but we're in 3 dimensions. I kind of don't have time. I didn't plan to write that stuff down, but keep it mathematical connection too. Okay, so now what is pitch? Okay. musical pitch. Okay. Okay, so I think we can kill this off, maybe. Kill that off. So, okay, so I'm going to subject you to some noises, I'm afraid, but that's the goal of today. So what I'm going to do is play a repeating sound, and I'm going to make it, so it's going to be something that repeats like this, and the time it takes to repeat is called the period, so I'm going to make that 0.2 seconds. Okay. So anyone tell me how many times it happens per second? 5. This is good. Great. You've got it. Okay. So the frequency is 1 over the period, right? So 1 over 0.2 is 5. And the symbol given for times per second is called hertz. Okay. So this just means times per second. Okay. So nothing is too elementary. And by the way, I want you to ask questions if something isn't clear. Because again, people are coming from all different backgrounds here. So let's play that. So I'm going to play, it's going to be a slightly annoying click sound, I'm afraid, but the point is to illustrate something. Okay, but this is a really useful formula. T equals, F is 1 over T. T is 1 over F. Okay. Okay. So that's a click. Do you hear individual clicks, or do you hear a pitch? You hear individual clicks, right? So, okay, so now it's going to get really annoying, I'm sorry. But what you can guess what's going to happen, right? So I'm going to increase the frequency of these clicks and turn it down so it doesn't drive you too crazy. And your ear still, and you can see the frequency there. Right, there's a number there, 9 hertz, 10 per second. I'm going to drop the volume, about 20 per second. Do you still, put your hand up if you have stopped hearing them as individual clicks. Oh, all right, and now I'm going to ask you to keep your, I'm going to ask you to put your hand up when you start hearing the musical pitch. That's amazing. Some of you interpret that as a pitch. That's good, it's good. But I'll keep going. So if it's a musical pitch, we should be able to tell it's one note and not another note. So let's try that again. Yeah, okay, you're all humming it. This is good. Yeah. I don't know what that is. All right, so that must be about an E. Okay? So you all agreed, actually, you could hum it, you could tell what pitch it is. So somewhere between around 20 and 40 hertz, we start to interpret things as pitch, not individual repetitions of something. And that's something to do with the neurons in the brain and the ear system that have evolved over, millions of years to be sensitive to things around us and keep us alive. So, go figure, and maybe music has been part of human culture for equally long. So maybe we've evolved to start hearing pitch. So I guess we should go to a pitch that's a little more well-known. So, sorry, I'll play. Okay, if some of you have perfect pitch, you'll recognize that that is a good C. Okay. So that's 65 hertz is a C. Okay. So I'm just going to write down, it's going to be a lot of numbers and frequencies for a while, but the amazing patterns start to emerge. Like, how do I make another C? So I'm going to slide it up to 130, someone said. There we go, 130, that's another C. How do I make another C? What was that? Okay. 260. It's painful. Let's do that. Okay, right. So that's a C. That's a C. That's a C. That's probably a C too. All right. All of those are Cs, right? we all agree, these are different Cs. The 130 one was called C3. This is sort of given, all notes have a music, in the Western system, notes have a name and an octave. Is it C4? Did I get it wrong? I think it's C3. No. That's 130. And then that's C3. And then I think that's C4, which is, anyway, so you get the idea. Okay, that all of these notes that are related by factors of 2 are the same. We hear as the same note, and if you ask someone, is it the same note in any culture in the world, they'll all tell you, yes, it's the same note, which is kind of peculiar. So, okay, so this ratio each time, right, as many of you know, is called an octave. So, and this means a 2-to-1 frequency ratio. Okay, so also, so the same note happens for all of these frequencies, right? So 65 times 2 to the power k, or 2 to the power n, for n is some octave number. It's all the same. These are all of these frequencies we hear as the same note. Okay. So that's interesting. Like I'm now tempted to do the really painful one, but I think it's fun. And that's for you to put it. And that's for you to put up your hands when you hear something. Okay, good. All right. All right. I'm going to put it on pure tone because that's really what should be done here. No, really? Wow. Is it really loud? No, good. Okay. That would be a shame because I can't hear anything. Okay, everyone's complaining. Okay, this is amazing, right? Some of you can hear at 14 kilohertz. I'm turning it down quite a bit. But, all right, now I hear it at around 11. There, it's quite, I'm not deafening anyone, right? This is okay. Yeah, I can turn it up a little, but, okay, but then that's the range of human hearing, right? Yeah, it wasn't that loud, but you guys are amazing. Okay, let's go back to the, and I'll explain what these different things are. Yes, that's what's going on. All that was a device to measure the age of distribution of the audience. Right? So, but yes, so I used to be able to hear old television sets used to have 16 kilohertz, scanline frequency, before any of these LCDs came along, and I could hear that. It was annoying, in your parents' house, and now I can't. I can only hear 11 kilohertz. So, yes, because the music has a lot of high frequency content. Yeah, definitely. So it's and adults don't notice. Okay, so but what if we notice something? Okay, so far all we've done is figured out that things that are not related by powers of 2 are all the same note. But let's make another point, and that's that musical intervals are frequency ratios. Okay, so I won't write that down, but what I'm going to do is play some more lovely sounds at you. Okay, well, I'll write it down. It's such a key statement. Intervals are literally frequency ratios. That is the most kind of key part of music theory. They're ratios. They're not frequency differences. That's the important thing. So let's do a demonstration of this. And you might want to know what frequency ratios are actually nice. So what I'm going to do is play, again, we're going to do it by audience, by survey, in a very unbiased selection of the world's population. And I'm going to put it on, okay, I'm going to play 200 hertz, right? So I'm going to play two frequencies, F1, which is 200 hertz, and we're going to start looking at F2 and vary that and start to note, and I want you to put your hand up to the degree that it sounds harmonious. Okay? So save a little bit. If you think something sounds nice, save a little bit for later, just in case something later sounds even nicer. Okay? So this is a tone generator. You can play with these things online. It's incredibly easy. And the great thing is, thanks to modern browsers with tabs, you can run 2 of them at once. So now I've got 2 tone generators going. Now I'm going to start. Sounds great so far, right? So you should all have your hands up, but that's okay. That was just a test. So let's. Pretty soon it starts to sound ghastly. Okay, right? Sounds ghastly. Okay, some people like that. Some people like that. That's good. Okay. 250 people liked. Sounded sort of. I'm gonna. Okay, so 250. Well, what's special about 250 and 200? What's the ratio? 5/4, right? Okay, so that has a musical name. Does anyone know the musical name? Major third, right? So this is, I guess we were starting in roughly G. So that's G to B, right? That's it's called a major third. Now, for those of you who are not musicians, you're gonna really wish they hadn't named things the way they did. It's really, right. So why is it called a third? Because it's in computer science what we call an off by 1 error. So what this means is that right, normally this is like if you start somewhere, then you've moved 0, right, and then you move 1 tone, and then so you're 2 tones away from where you started. That's why it's called a third, right? Because because you start counting on 1, 1, 2, 3. And that's literally why it's called a third. Okay. Okay, so let's keep going. Okay, you like that one. Oh, some people like that one too. Okay. So 266, 267. Okay, ratio? Someone tell me? 3/4. Right? It's actually 4/3, right? So, okay, so this is called a perfect fourth. Again, off by 1 error. Okay. But if you like that one, you'll like the next one. Ah, so nice, right? Okay. Right, so 300 also sounds even nicer, right? I would claim it's sort of more consonant, 3/2. Okay, so this is also called a perfect something. You should be able to tell me. 5th. Okay, because it's 4 notes apart on the white keys on the piano. If you start in a key that in certain keys, I mean that's just it's just a convention, right? But that's what the intervals are named, and you know you have to live with it. As a music theorist. Okay. And then it gets really nasty all of a sudden. That's really nasty, right? That's not so bad. Then it kind of gets nasty for a while. I'm not even going to look. You tell me. Okay, right? Sounds great now. Okay, so and you already know about that interval. That's the octave, right? So we don't need to do that one. Okay, but there was another one that happened, right? 320 was pretty good. That was, I can write the ratios as, so that's 5/3, but you might write these things as 5/3, like this, to illustrate that it's one integer divided by another integer. Okay, well that's really peculiar. Why on earth does it, why is it integers? Who invented the integers? Pythagoras. Yes, you're right. I thought someone was going to say God, but Pythagoras is good enough. Okay. Okay. So this has been known an extremely long time, and Greeks figured this out by varying the lengths of strings, and I don't have time to really tell you why the lengths of strings are proportional to the periods, and therefore the inverse of the frequencies. But Nilam actually talked about that. So the Pythagorean, like his followers, and then the people in the Renaissance who rediscovered all of this, they didn't really like ratios involving numbers any bigger than 4, integers bigger than 4. So even 5/4 was considered blasphemous. So that would be just not, not allowed in early Renaissance music. But, perfect fifths, perfect fourths were all good. Okay, so, and what's interesting about this picture, you can see, this is a woodcut done in like 1492. So, it's all been mangled by, 2,000 years of people passing ideas on, and there's weights of different strengths here. We could talk about how the tensions in the string affect the pitch. Would affect the pitch, blah, blah. Anyway, it's kind of interesting. The picture doesn't really get the math right, but it shows you what they were up to, and that the math of these ratios has been known for extremely long time. It's kind of amazing. Okay, so why do we believe that ratios are the important thing? How would someone devise it? What if I came along and played devil's advocate and said, well, actually, I just think that adding 100 hertz to any interval makes it a perfect fifth? Someone tell me an experiment that would prove or disprove that.
800, 900.
Yeah, let's do it. Sure, 800 and 900. I mean, I was going to do 300 and, yeah, so, but it's all good, right? Just pick any other frequency. 800, and let's see if 800 to 900 gives you a perfect, perfect fifth. 900, I think you could even type here. Yes, you can type. Okay, that's not a perfect fifth, right? That sounds a bit like a whole tone, a major second. Okay, for reasons we'll get to, 8 to 9 is going to come up very shortly. But if you want to make it a fifth, you just slide it around until it sounds like a fifth. And you realize it's not problem. So it's always ratios, right? Which is weird. Ratios, right? Not differences. It's kind of amazing that our ears are actually computing the ratios of two frequencies all the time when you're hearing things. If you have any musical training at all, then you are sensitive to the ratios. And in fact, even if you don't have musical training, right? So, and now you know their ratios, we can start doing things to the ratios, like stacking them on top of each other. This is what mathematicians like to do, right? If you take any operation, then you want to see all of the different things you can get by combining that operation and see where it gets you. So we're going to combine the ratio of 3 to 2, the perfect fifth, and see where you go. So let's start with C, just to pick a concrete number to start with, right? Okay, so that's C to G. All right, so combining ratios. Well, we could call them stacking it. Stacking ratios. So, well, stacking intervals. So C goes to G, and this gap is, this ratio is 3/2. So, well, G is a useful note. Let's say all you had was C, and then you generated G by having this nice thing that you've observed by plucking strings or just being Greek. And right, you've now you're like, well, it'd be nice to have a piece that's in G. So now we need a fifth from that. Right? Because maybe you want to start in G and be able to do that lovely perfect fifth interval again and again. So you're going to go, and this note's called D, and it's a D just a little bit above, an octave above the original one. That also has to be 3/2. Okay, so you can keep going. Okay, so but what I didn't say What did I not say? What's the ratio between C and D? This C and this D? 9/4, right? You're going to combine these two ratios by taking the product. 3/2 times 3/2 is 9/4. Okay, so that's how musical intervals combine if you sort of start piling one on top of another. So now we can go to the next one. What's the next note? Some of you know this. A. Okay. Okay, so that's going to be another 3/2. Okay, so if you want to go all the way from C to A, then what would that be? 27/8, right? Which is 3/2 cubed. So stacking the ratio 3 times. Okay, this can continue, and pretty soon, right? Sorry, loud. Okay, we get to F sharp up here, and then this keyboard runs out. But here's one I prepared earlier, as they used to say in the British TV shows. Okay, all right, so this is what happens if you have a grand piano and you do that. You keep going. We made it to F sharp, but then you can go C sharp, G sharp, D sharp, A sharp, or B flat. These notes have other names, and you sort of come around the backside of what's called the circle of fifths. But the point is that in the Western classical system, we have names for each of these notes. They're each supposed to be a fifth apart from each other, meaning, you know, you sort of work in whatever key you're in. You would actually be skipping 6 notes of all of the white and black notes each time. So we'll get to see why. But eventually, you're supposed to come back to the same note, but in a different octave. Okay, I'm glad you found that distressing. That's interesting. Okay, so, okay, good. I was expecting that spontaneous reaction. Good. By the way, so these first 4 notes are how you tune the cello, right? So these are really important for string instruments. These notes is how you tune the violin. The bass is different. The viola is like the cello an octave up. Okay, but yes, somebody is upset about that, right? You're eventually going to get to C, and this is C supposed to be. This is supposed to be the original frequency. But the ratio to the original is supposed to be 2 to the 7, which is, as you know, 128, right? 7 octaves you've gone up. I mean, you can just sort of count the octaves if you want. Just the green dots count the octaves here. Okay, and now, but supposedly you're supposed to have also gone up 12 times using 3/2. Okay, so this is also supposed to be, if you go all the way over to this, should be 3/2 to the 12th. Okay, and what is that number? Well, I won't make you compute it on the fly, but it's 129.75 ... Okay, so it's pretty close to 128, right? But it's not 128, and it's a very elementary proof that you can't have, for this to be equal to that, you'd have to have 3 to the something equal to 2 to the something else. That just can't happen, you know, just basic number theory. So something's gone wrong. You could interpret it, something has gone wrong with a harmony system. What's the error? Right, the difference is roughly 1.4% too big. Okay. So it's not a tremendous error. That's actually about 1/4 of a semitone. So it's not even something that many people would even recognize, like as a musical difference. They might just say it sounds a little off. But so what do musicians actually do? Right. So this. All right. I should just say, cannot be equal. Not equal. All right. Cannot be equal. We cannot match these guys. So, okay. Let's send that up here. So what does the sort of agreed convention these days, or at least for the last 100 or so years, at least in Western classical music, at least if you don't dig into too many details, right? There's a lot of brushing an awful lot under the rug here, is that there's a compromise is made. In tuning, if I could spell compromise, and do I have something to show? So the compromise is that we want to have a ratio that isn't quite 3/2, because it can't be, but which gets you back to the number, to the letter name C at exactly 128 if you take 12 powers of it, right? So the compromise is you say R is the whatever our new fifth is going to be, right? I won't call it a perfect fifth anymore. It's going to be slightly imperfect. But what you want is that if you do go up 12 of those, then you go up 7 octaves, which is 2 to the 7. Okay, and then you just have that's a math equation you can solve. R is 2 to the 7 over 12. Okay, and roughly how big is that number? 1.498, roughly, right? Which is slightly less than 3/2. Okay, so this is a system, and you can like it or hate it, but it's commonly used because we have to have we want to be able to play in different keys and not have different keys preferentially treated. So this is actually called equal temperament, so that means all intervals are treated equally. Why would Pythagoras not approve of this ratio? Not only is it not a ratio of small integers, but what kind of number is this? It's a rational number. So it sort of breaks all of the rules, right? And you can hit, so you might immediately say, well, who cares? Does this make a difference? I think I did type this one. So let's go back to 200 with this guy. And if you do it for this number, 1.498 times 300, I worked it out, 299.66. So do you want to know if it sounds that different from a perfect fifth? Yeah, it sounds like, every musician would agree it's a perfect fifth, but there's some weird kind of phasing things going on, right? Okay, compare that against that, where they're totally locked in, right? They have a different feel. So, but that's the compromise we've settled on, is actually most musicians use those, if they're all going to play in tune with various different instruments, they all use this equal temperament system. And I can play a little, what it does is it makes certain keys privileged, like if you agree that you're going to start with exact Pythagorean ratios starting with C, then chords close to C sound nice, chords far away, like F sharp minor that I'm about to play you, sound horrible. So if you use Pythagorean intervals. But if you do it to equal temperament, everything sounds equally slightly off. But it doesn't, because we're so used to it. So have a listen. Okay. It sound off, right? Okay, so what you're hearing there, right? This is just intonation, and that's the name given for Pythagorean intervals, like 3/2, and a scale that's built that way. And by the time you get to F sharp minor, it sounds horrible. The ratios will start to grate against each other and not work. So the compromise is equal temperament. Let's play it again. Those sound nice. They sound bad. So the last ones sound like what a normal instrument would be tuned to, like this. So, great. That's kind of what we're used to. But string players still like to tune to 3/2 precisely. And then that causes lots of confusions with other instruments all playing in the same orchestra, everyone gets mad. So, you know, that's some of the stuff that's going on. So this equal temperament system is based on every semitone, right, which is the smallest interval you have in Western classical music between 2 to the 1/12, which is about 6% above 1. Okay, and what else was I going to say? Well, there's a really deep philosophical question here, which is why are there 12 keys? Why do we have in the octave, right? If like when, you know, if I count, so not including the ends, there's 12 semitones in the octave. So why 12? Okay, in an octave. Well, sort of the fundamental reason, if you just take this reasoning here, it's that we like exact ratios, like low integers, like 3/2. They sound great for reasons I'll hopefully mention a bit later on. And we like octaves, really, we like them a lot. So those two systems have to mesh, and it's the kind of 12 is the first number where the systems kind of come back and lock in again. And the kind of fundamental reason is that log to the base 2 of 3 is very close to 19/12, which is just some arbitrary set of integers, right? And this is it, and the error is the relative error. Now I'm talking as a numerical mathematician, is 3 digits. So you're off by 1 part in 1,000. And that is a sort of number theory reason that there's a low, just coincidence in a sense. And if you take that statement and just apply it here, you'll see that that's equivalent to saying that if you got 9, you know, if you got 7 octaves, then you'll almost hit 12 powers of 3/2. Yeah.
Arrive at continuous fractions.
You could write this as continuous fractions. Yes. There's a lot of math books that, believe me, people go nuts on this stuff, and they push it to all sorts of like approximation theory. And you can say, oh, but there's another system where if I continue further and include like 53 notes per octave, then everything can lock in even better. And I thought, should I play some sounds that were made with instruments, you know, with tuning systems that involve 53 notes per octave? And I thought it's right. They're never used around the world. They're just sort of mathematical abstractions. So, but that's kind of the fundamental reason. Now, these 12 semitones, not all musical scales around the world have them. There's, jazz, jazz and blues are based on all different scales, And there's sort of Middle Eastern scales, So different scales where only subset of the semitones are used. Oh, in fact, then the Greek ones, some have notes that are sort of halfway in between. There's a flattened, there's a really flat sort of third. I can't do it. If you can kind of half press a note, you can kind of bend it down. So there's a lot of different cultural things happening, but I'm trying to give you the big picture. So, okay, so amazing fact is that this sort of thing about that we hear ratios means the following, and that's that here's the piano keyboard, and here's all of the notes that you would write out for the white notes on the piano keyboard, and here's all the frequencies, and we write this, that this looks like a beautiful linear graph, right? Each note has equal spacing. We kind of have a feel, the way they're placed on the keyboard. You move the same distance. It's, you move the same interval. So here's the graph. What we call, mathematically, the frequencies are growing exponentially because it's all based on ratios. And that means our hearing actually is the log of the frequency. That's the way our psychoacoustics works. That's not really a math statement. It's just something amazing about humans and animals. I don't know. But, okay. So let's go to some pure tones now and play you some more notes. So we're going to get into a little more of the physics of decomposing sounds. How long have we got? I mean, I can keep going for a long time with this stuff, so you're going to have to tell me when to stop. It's 4:20, so we've got, I'll definitely go for another 10, 15 minutes. So, pure tones, okay. So far we just talked about pitch. So, there's certain instruments that we've designed that make a special sound. Here's an example. Maybe I either damage this or your table. I'll damage this. All right. So let's record a new sound. Where's Audacity? Okay, it's got to boot up again. Here we go. Record. Gonna hit this. Okay, that's a special kind of sound. Let's go into a section of that. Zoom in, zoom in, zoom in. Okay, look at that. Isn't that an amazing graph? Okay, someone knows what that graph is. By the way, there's two of them because it's left and right channels, but don't worry about that. Okay. Somebody must have seen this graph before. I have a feeling. Okay. Has anyone seen it before? I don't know. Okay, actually, I'm going to label this as theta. That's a really big clue. Okay, so what's this a graph of? Sine, okay, sine theta. Okay, so what you're seeing is actually sort of a scaled version of that. And sine theta, recall, is the height. I messed up my board work. If I did this in Dartmouth teaching seminar, they would not be happy. I would not be happy. So what you're plotting is the angle, is the height of a point on a unit, on a little unit line, rotating around the origin, right, at an angle theta, and that angle is growing in time. Very peculiar. Why on earth would some lump of metal, which is sort of springy, produce something to do with the sine function that's to do with the height of a triangle with a hypotenuse of length 1? That's totally mind-blowing, I find, right? But it's true, and the mathematics behind that. So let's write out a pure tone. A general pure tone is pressure. Remember, everything in acoustics is pressure versus time. It's sine, okay, and we've got it's sine of something t, and then I'm leaving some gaps here. Okay, you don't know how loud it is, so you've got to give it an arbitrary amplitude. The frequency, if we want this to be a period, which is 1 over the frequency, then you actually have to stick, you can't just put ft, but what do you have to put? What's that? 2 pi. Just because the sine repeats every 2 pi. I forgot to label this, that would have helped. Yeah, right, okay. So in radians, 2 pi, okay, and then, actually, you don't know what time it started exactly. It could be that the time axis started here instead, and then so you have something called a phase shift that lets you shift the graph around, right? So this is the frequency, this is the amplitude or the strength, and this is called the phase shift. Okay, so the reason that I don't have much that I can say in detail other than that a lot of these systems that vibrate, like tuning forks, but and individual vibration modes in other more complicated objects, each vibration mode obeys Newton's second law, which says force is mass times acceleration. So y double prime might be the position of something. So the force then is being restored by a spring. So I'm just going to write down, I'm going to do a bit of intimidating math just to give you a flavor, right? So this is the second derivative of y with respect to time, times the mass is minus the force times the position. This is something called an ordinary differential equation, and if you solve it, then you get this with some formula for F. And A and phi are up to you. But that's the kind of math of, this is called a mass spring system, and it occurs whenever there's an object that likes to be pulled back to where it likes to be, but that object has some mass as well. So that's kind of why pure tones arise, but they happen to be extremely useful. All right, I'm just going to have to cover it up. And we're going to go back to this one. They happen to be extremely useful because mathematically they sort of are the components that build other signals. And so what we're going to do is play with a tool that now lets us build sounds out of pure tones, and those pure tones are going to have certain frequencies. So we're going to build sounds like some periodic signal that I don't know what it's going to be, that has a period of t, which is 1 over the frequency. Remember, this is p of t again. That is supposed to be built from some pure tone with what's called the fundamental frequency. So let's just call this f again, plus some phase shift. Okay, so that's the fundamental. And then, all right. And then you're going to add more pure tones that are actually just the integer multiples of that frequency. So I'm going to put 2 pi times 2f here, so it's clear, times t, and then phi 2, and then plus a3, dot, 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 and this is going to be 3f, and so on like this. Okay, and this is a way to build a periodic signal out of component pure tones, and it turns out you can build any periodic signal you want, with a little caveat for the mathematicians in the room who know about like L2 spaces and like L1 and all of these like spaces that mathematicians are so unnecessarily obsessed by. So I can't make this much bigger, sorry, but like what we've got here is I can draw any graph. This is a beautiful applet written by somebody, physics guy. So here's a graph. He's called Paul Falstad. I'm going to play some sound. Okay. So that is what that sound sounds like. That graph played at a repetition rate of, I don't know, probably 440 or something. Okay. And this here, these dots are the different amplitudes. And now I'm going to vary the different amplitudes, A1, A2, A3. Right? So that graph has the dot A1 like this, A2, A3. How high that graph is tells you how high that component is. Okay. So there's bringing in a lot of A2 and then zeroing out A2. Here's A3.
What's the green graph?
What's that?
What's the green graph?
Oh, the green graph, I don't even know. I don't see a green graph. The red graph,
If you move it around a little bit, there it is.
oh, I don't know. It's one of the components. Yeah, there you go. It's one of the components. It's separate. Okay. Can you hear that one coming in? And then here's the 5th one. No, that's the 6th one. Okay, right? I can add and there's the 5th one. So the amazing thing is that when I bring each of these components in individually, you hear them individually, like that, right? Or the 9th one's really cool, listen. Okay. Okay, you hear that individually, right? You can hear that little whistle. And I guess, I don't know if I can even play it. But yeah, I guess it's somehow in B flat, I don't know why. But you're hearing like that one component. But now, I'm going to play it, I'm just going to switch it on. And do you hear that component? You can if you're really good, but most of it, you just hear it as a buzz. And if I draw a different thing, you hear it, your brain fuses it together into a single tone. There's a different one. There's another one. That sounds a little more like oboe-like or something, or like bassoon-like. right? So all that we're doing is varying all of the strengths of these different harmonics, they're called, and you get different timbre with the same pitch. So timbre is just the strengths of these guys. So this set of strengths is literally what controls musical timbre, equals timbre. Okay, so there are more subtle things like how the timbre changes over time, but that's the basics of our ear measuring those different components and fusing them together to one sound. Our ear just hears this crazy graph. Because it's periodic, it hears it as one sound with a certain pitch. So, okay, so maybe the most important thing to say about that, no. Here's a nice demo, because this thing happens to generate the harmonic series itself. It's kind of complicated to explain why, but you can. Now, question for you to the musicians is, which notes are we hearing in the harmonic series? Like this lowest one. Is that one? Is that the fundamental? Well, I'm going to go up to the next one. That's a fifth above it, so can that first one be the fundamental? And then here's the next one. All right, and this is the big giveaway. Which one is this? Right? So that what's that? It's a tenth, yeah. So that's like a major third stacked on an octave. So that has to be involved in number 5, that top one you heard. I don't know what key we're in. I guess it's in roughly somewhere between G and A flat. Let's pretend it's G, right? So we were hearing, but the fundamental is actually down below. And you can't excite the fundamental with this. You can hit it and you can kind of hear it, but it's sort of absent. But it's to explain why the wind blowing over the edge of this thing only excites one of the what are called underlies of this pipe is a non-linear physics problem. I'd actually love to understand it. I don't. If someone knows more about why this happens, I'd love to know. Yeah. It's a normal pipe. I don't think the fact that it's got ridges matters, but one end has to be moving relative to the air, right? So I don't think it matters that it's rotating. You can do it the other way around, so it doesn't need to have a special shape. The length matters, because that determines the pitch. So, yeah. So there's a lot going on there related to PDEs, but differential equations, but I was just going to skip it because it's a fun harmonic series demo. So, okay, but I want to show you this tool that I had on if you were in the audience when you were just coming in, which is it's a way to measure what we just did with something called synthesis, putting together sounds, and that applet is from Falstad, and putting together pure tones that have all of the integer multiples of some fundamental lets you build a periodic signal. And you can also decompose, so to kind of do the opposite, which is to, let's put, oh no, I didn't want to start that one. Please die. Okay, thank you, GL Spect. Okay, so this is a, oh no. Oh, it worked, okay, good. All right. Okay, so this is a tool that I wrote in C and glut, some old code that lets you do OpenGL, but that's why it's a little finicky. So I'm going to change the colors. So what this is showing, I'm going to speed it up a little, and maybe actually I'm going to show it a slightly different frequency range. So it's going to show 0 to 6,000 hertz on the vertical axis, and time is on the horizontal axis. So you can see seconds are scrolling by, and what it's doing is decomposing the sounds that it's hearing in little intervals of time into their component frequencies and plotting them as brightness where they are loud and just leaving it dark where there's nothing. So if I just change that a little, okay, maybe that's a good setting. So you can see it's analyzing my speech, which is going to be another interesting thing, but I can run this applet at the same time as this thing, and you can see that it's actually showing the same thing in a different way. So let's just do that. God. No, go away. All right, it's just all about moving things around on the screen, isn't it? Let's put that there. Go back to the Falstead app. Well, you can kind of see it. Okay. All right, let me bring in number 9. Oh no, that's number 8. You see it gets much brighter here every time I do that? So it's like a brightness indicator of what could be shown on a graph, as it actually is down here. This is kind of a graph of A, the amplitude, as a function of frequency. Sorry for the sounds. Okay, but that's a horrible sound. But right now, you get the idea that it's showing the same thing, except it can do it for any period I want. So I can switch that off, and we can listen to other sounds and verify that the different strengths correspond to different timbres. So I'm going to play something I stole from a YouTube video, and you're just going to hear some different. The guy will introduce the instruments, and you'll see the different timbres.
An acoustic guitar. An upright acoustic bass. A banjo. An upright piano. A clarinet.
Now, clarinet has the odd partials.
A violin played pizzicato, which means the string is plucked instead of bowed. A melodica.
Notice it's a lot of
A
high,
side-blown flute.
different pitch, but it's different octave.
A mandolin. A whistle. A sitar.
Okay.
And lastly, a saxophone.
All right. Pretty cool, right? Right. So what's going on? You're seeing different strengths, and for each of these, indicated by the brightness, that controls the timbre. The clarinet was very heavy on the odd numbered 1, 3, 5, 7. That's something to do with the ODE in the shape of the clarinet being a constant bore, and you can analyze eigenfunctions and eigenfrequencies of a tube that has one end closed and the other open, and understand all of that kind of stuff using math.
So, the flute seems to be missing every other harmonic.
Yeah, that's weird. Oh, no, the flute jumped up an octave. That's what it is. So it was missing them, but they're actually playing. You won't believe how long it took me to find, I don't know how to search for all instruments playing the same note one after another. It's quite hard, and I managed to find this guy who'd done it for me, so nearly got it right. Pretty good, you know, they're almost all the same octave, but that's what it was. It's a different octave. Okay, so that's what timbre is. Human sound, human voice also has timbre. So I've overrun a little. I hope you let me just finish off a little. I'll just tell you a little about the human voice by doing a little, I guess, demo myself. Okay, so I was singing the 5 vowels. The only difference, other than me wobbling around, is that there are different frequency bands that are exaggerated. Like here, there's a lot of stuff around A and E around 3,000 hertz, but then that sort of shifts down to like 1,000, but there's still some other stuff for oo. It's actually a little harder to tell. What my mouth is doing is providing a filter to a periodic sound that's coming out of the vocal cords. For those of you in math, that's called a convolution of the impulse response of the sort of acoustic cavity of the mouth with the signal, and that's why it looks like the product of a bunch of delta functions, lines, with a filter function. That's the convolution theorem. For those of you, I'm now like talking gibberish for many, but that's for the math people. There's a whole bunch of signal processing and convolution theorem happening here. It's much easier to see what filter function I produce by whispering, where I'm not producing a periodic signal. Okay, I was going to have someone volunteer to do that, but you have to be kind of aggressive about it. Right up, and you've got to get up in the mic. But look at these different formants are different frequency bands that are actually how we understand vowel sounds. So the fact that these two are closer together for oo rather than like o and things like that means that you're able to distinguish vowel sounds whether they're sung or spoken. So I don't know. I think I'm running out of. I don't want to overrun too much. I could leave the other stuff. I was going to talk about beats and play some more stuff, but I think I'm going to call it a day because I've overshot by a little. And just to conclude, and we can, if you want to stick around afterwards, we can do some more demos. But was I going to play? Yeah. Consonance and dissonance is built into different chords. But if I play a jazz chord, or okay, there's a lot of lines, frequencies that are hitting each other very closely, and that kind of controls whether something sounds consonant or dissonant, but it's very culturally shaped as well. I think that's all I can say about that. And I'll just conclude and just say there's a whole bunch of math in all of these aspects of music and sound. There's a whole bunch of stuff I didn't talk about: waves, rhythms, resonances, differential equations, and algorithmic music. There's some things you can play around with yourself, and I really recommend that. And here's two really good books, and thanks to my thesis advisor who kind of got me into this topic, Eric Heller. So, thank you.
All right, so thanks a lot, Alex, for such a wonderful talk. Let's open the floor for questions. Yes?
When we have the frequency decomposition of the instruments,
Yeah.
all the high frequency modes seem to die off faster than the low frequency modes. I was wondering if you could explain a bit of why that happens.
Oh, that's a good question. I don't actually know. I think it's to do with losses in the metal. So, you know, you can take any object that actually has different component frequencies and look at how they die off. So here's a little bell. So as you... Right, so you can sort of see that the high frequencies die very quickly, and these ones last a bit longer. I think it's because of dissipation in the metal, that it's slightly damping inside the metal, because there's no reason the high frequency should radiate better than the low frequencies, right? So yes, I think it's something to do with actual damping in the metal. So here's another one. Right, you see, there's a whole bunch of not harmonically related modes here. Each is an eigenmode of the object, and they each have a different decay rate. And I think it's to do with properties of the metal. So, Sure. We didn't even get to why that doesn't sound like a certain pitch. So anyway, yes.
I really enjoyed this and I understood it more than people.
Okay.
I have two one-sentence stories that maybe enjoyable to tell. One, I have some issues with my throat, and so I see it. I saw it in English, I put something and then take it again. You can tell this. At the first appointment, she said, I want you to explain how you think voice works, and I know you're a mathematician, so you're not allowed to use the name Fourier.
Oh, yeah, I use Fourier. Okay. That's tough.
The second, a few years ago, I was explaining to my dad, who's not an mathematician, he called me from the landline when he needs to use Microsoft Excel. I was telling him about dark tracks in the shape of a drum, in the spectral theory.
Okay.
He was quiet for a moment, he went to the stereo and put on the band, the bigger old Dixie band, we went home singing. As soon as he started singing, he said, I'm hearing the shape of a drummer.
Okay. Right. Yes.
Goodbye.
Okay. Thank you for the bad jokes. This is. Any other questions?
Change the medium
Yeah. Change the medium.
where the sound is played. If it is underwater,
Yeah.
the kind of pressure of the atmosphere plus the column of water above the sound.
Well, so water is a bit different. It's incompressible, whereas air is compressible. But well, it's much harder to compress water, and it's much heavier, much denser. So it's maybe 10,000 times harder to compress water than it is air, but it's about 1,000 times denser, and that results in the speed of sound in water, right? The speed of sound in air is 340 meters a second. The speed of sound in water is 1,500 meters a second. So, but it's the same kind of wave. It's transmitted by compression and rarefaction the same way, and pretty much does all of the same acoustic things that bounce off stones. The only difference between air and water is this. There's a big that ratio of everything means that one doesn't couple into the other very well. So it's actually quite hard. So you have to have a special microphone or hydrophone that couples directly to the water. You can't have like a blob of air in the way. It just won't pick up sound.
I'm thinking about the detection of a submarine.
Yeah.
This sound.
Yeah, it's just pressure waves, the same thing. So a scalar wave satisfying the three-dimensional wave equation. Yeah.
Okay, well, with that, join me in thanking Alex for
Sure. Thank you. Okay, sounds good. But if anyone wants to come and chat to me, I'm going to stick around or play with any of these things for at least the next few minutes. Yeah, sure.
When you were using the equipment before, I saw that you placed a metal in front of it.
Ah,
Is that
so it's a half wavelength resonator. It's a half wavelength resonator. So it's kind of magic. There's a lot going on here, right? This thing, right? But so it only excites it when it's near it, but it makes it much louder. You can also do it by direct transmission, but it's not as good. It just doesn't work so well. But this is a nice object. This bit is actually its own tuning fork. But and then you can get beats. Like I can do beats between this one and this one. Okay. I was going to get to beats, but
so this is not just any piece of metal that I saw it.
No.
It's a regular piece of metal.
I don't know if you can hear that. It's not great, but yeah. So this is it's a neat little amplifier. That means I don't have to connect this to something like that, because it can either be transmitted by mechanically or just by exciting this air column. So what's going on in here is that there's a graph of pressure versus x. It looks like that, right? And then this thing is actually flapping up and down in time. So, and this is called a half a wavelength, right? So if you work out, if you use this speed of sound in air with 800 hertz, it doesn't seem right, does it? It seems a bit short. But maybe 8. Yeah, I don't know. It's supposed to be half a wavelength. So, all right, I'm not actually sure. Maybe we should think, I'll try and think about why it resonates. I'd assumed it was half a wavelength long, but now you're getting me to rethink that. So, right, yeah. Okay, good.
And also,
yeah.
Can I play with your pipe a little?
Which is the pipe? This? Yeah, go for it. Yeah, sure. See if you can get it to stick to just one pitch. That's the thing. Yeah. Hi.
Maybe just a technical question related to the first.
Yes?
On the
Let me just...
how the energy of the wave or the amplitude of the wave? Like
well, it's a log scale in color, probably, anyway. So it doesn't matter, but it's the amplitudes are all non-negative numbers in this way I've written it. So you could really be plotting their square or just the value.
Yeah,
but if you're used to complex, you know, I'm not sure what...
When it kind of decays, when you're talking about decay,
yes.
like they should factor in like how you represent them. Right?
Yeah. This is just for a frozen periodic sound that goes on forever. In real life, things change over time as well, and you actually have to there's an uncertainty relationship that says how much frequency resolution am I going to get? You have to measure for a longer time if you want to get more resolution and frequency. I don't know. Yeah, there's some math there, but yes, but they can change over time. But it's sort of that's Fourier's original way of writing was just for a fixed periodic signal that just goes on forever like this. But yeah, but it's a good approximation, and then you've just got to break it a little for when things change over time. So, yeah.
So I'm still this instrument.
Sure, yeah, it's fun, right?
Last time when you showed it, I thought you were making the noise from somewhere else.
Oh, okay, you didn't believe it. Well, you can buy them probably on Pasco, right? I bought a lot of my physics demos at a company called Pasco. Anyway, so those are...
So this side is not even closed. Initially, I
No, they're both open.
it's just a normal pipe.
Now, this is a half wavelength. I can guarantee that is the correct pressure pit for the lowest mode. That's what the pressure looks like.
And this is just a pipe of size.
And the next one is like 2 half wavelengths, and then 3 half wavelengths, and so on, right? So, yeah. Okay. I'm going to keep asking. Yes, hello.
I just wanted to say it was a really good lecture.
Thanks, great.
I don't have specific questions, but my
Okay.
background is in math, and
Okay.
I'm just starting to learn the piano.
Oh, great.
This was an amazing introduction to that.
Good, great.
Amazing.
Well, I hope you just start downloading some of these, like, just applets and programs and
Oh, no, for sure.
and start playing with them.
The books as well that you suggested.
Yeah.
But I just want to say this is really good.
Great, thanks so much. Good luck with everything. Yeah. Okay, great. Thanks a lot. Yeah, sure.
So is this slide available somewhere on your website or something?
The
so that I can play with
slides,
the links?
yes, I'll make sure the slides are on the website, and they may host them here as well. But yeah,
Thank you so much.
right, sure, good, enjoy. Yeah. Hi.
Hi. I had a class in my first year that was called Physics 2.
Yeah. Oh, so you did all of this.
We did a bunch of it. We
Okay.
didn't do the like circle of fifths.
Okay.
So that was really cool.
Okay, right.
But I was curious, in that class we talked a bit about a Helmholtz resonator, but
Oh,
not a lot.
right.
I was wondering if
So what? Yeah.
you have.
If I have any. Oh, I mean, I don't.
Yeah.
All right. This is a Helmholtz resonator.
Yeah. Is that
Okay.
something that's happening there?
It might be that. Well, no. This is different because this is like a whole number of half wavelengths along the length. You know, 1, 2, 3. So that tells you the pitch. This is different, and the pitch is controlled by the volume and the neck area and the neck length. And so it's a rather more subtle relationship, involved with because so this is like a one-dimensional ODE really. This is like the mass is a small plug of air here, and the spring is the volume of air. So you can kind of imagine, and it's all slightly amorphous. In the end, you actually end up solving a Neumann, what's called a Neumann eigenvalue problem, or for a domain that would be the surface, the sort of re-entrant surface, with du dn 0 on the surface, and it satisfies the Helmholtz equation. So same Helmholtz, but and then you could use that to predict the frequency. So yeah, that's the theory of Helmholtz resonators. I didn't get to them, but yeah, they're a little harder to explain. So yeah, right, sure. But yeah, I'm surprised. But you did them, and you didn't do them in the class. I'm surprised.
We mentioned them very briefly, but it was like also for non-math people.
Right.
At that point, I was not a math person yet.
Right.
And then after
Yes.
that,
Okay.
I became a math.
Okay, good. I'm glad it worked. All right.
Yeah. I was captured. Now I'm stuck.
Good. Okay, good. Right. Sure.
I have a question. It only occurred to me after the Q&A
Sure.
there.
Yeah.
I'm a musician, a mathematician,
Yeah,
but
yeah.
so I know that the unequal temperament, Renaissance, they had different keys had different affects. And they
Yeah,
used that
yeah.
basically, and then Bach's 12 type of clavier.
Right.
The thesis
Yeah,
on
there's
that.
so much about tuning systems that I just scratched the surface. Yeah.
And then equal temperament eventually.
Does it matter? Yes. I don't really know how much it matters these days, but yes. Yes.
I'm wondering, have you imagined a future of a new temperament?
Well, no, because there's so much bending that musicians do anyway, and most instruments you can bend, right?
Yeah.
Apart from the keyboard, or basically apart from percussion instruments, you can't do much with them. The keyboard and the even violin, even really open strings you can't really bend, but everything else you bend with your finger position. So it's all cultural. And the amount of vibrato and that's going to be added, and the nuance that's put, and sometimes you want to give a chord like a minor chord, like especially sad feeling, by sort of really flattening a third. I mean, I don't think there's I think the mathematical sort of obsession with trying to systematize and come out with the perfect system is a bit misguided when it misses the idea of free expression, right? So that's my view.
It's applied mostly to the keyboard.
Yes, right, sure. And but let me tell you why. You can't just go around devising mathematical ratios as the way to tune a keyboard, like a piano, for instance. And that's that the partials, so the vibration modes of each string separately happen not to be precisely integer multiples of the fundamental. And that affects the way you tune an octave in a piano and makes it slightly wider than an octave. It actually sounds flat because the partials don't line up. And by the partials, I mean that they're actually, it's this thing called stretched partials. And that's because the piece of metal that forms the piano wire, it's not a perfect string that obeys the wave equation. It has it has an elasticity. It has a bending. It fights back bending, and that causes the higher partials to be, it might be 1 times the fundamental, 2.01, 3.05, 4.1. They'll just get further and further off the higher up you go. And if you ignore that, the piano will almost sound out of tune, even if you tune it to perfect octaves. So that's the kind of complication that you get into with real instruments that makes the math sort of irrelevant.
Right. The ear is
Yeah, not irrelevant, but you have to really do the engineering to understand why, why a piano is tuned wider than an octave. So yeah, but that second book I pointed out has a lot about tuning systems. It's got crazy obsession about it. The one that has a free PDF. So Music, a Mathematical Offering, has a lot of tuning systems in it. So yeah.
Wonder, curious of the future, because
Sure. Yeah.
things are in fashion for modes, physical modes.
Yeah. Well, it's all going to get. Well, it'll be put out of work by AI anyway. So yeah. Anyway.
Do as much as we can.
What's that?
We have to do as much as we can.
Yes, sure. That's right. Yes.
2 more years to prove.
Yes, that's right. Figure out a new job.
Thank you very much.
All right. Good to meet you.
Thank you.
Did you have a question?
No, just thank you for the recommendations.
Sure.
That was just delivered like an hour ago.
Good. You ordered them. Good. Which, the first one?
Yeah.
Yeah, great.
Check them out.
Yeah, and Garrett's a friend of mine, so I hope you, drop him a line if you have questions. It's a really good book.
And I saw them even put on the website too. You people this.
Yes, yeah.
Another as well.
Oh, really?
Yeah.
Oh, jazz, then?
No, well,
No, church organ, gospel,
yeah,
okay.
well, I can show you.
I love Hammond. Yeah, I mean, I have a
my parents.
Nord Electro. Wow. Oh my God, you're serious?
Yeah.
This
it's
is
beautiful.
for real.
And well, remember I told you my dad was a drummer?
Right. This is the whole studio. Wow.
Yeah.
Oh my God. So you could.
Dennis Chambers inspired.
This is yeah.
Yeah.
It looks like Jacob Collier's studio, if you know him. Do you know him? Okay, he's an amazing British young multi-instrumentalist. Yeah.
But yeah, that's any procrastination. And then
Yeah,
keyboards,
the Hammond.
mother's keyboards.
Oh no, I have the Nord Electro. I have that. Yeah, because that's got a decent Hammond sound,
Yeah. So,
including a decent Leslie simulator. But you probably have the real Leslie.
yeah.
Yeah, that's crazy. That's a lot of.
Oh yeah.
That's a lot of maintenance. Keep all those going, and then you never move them
No,
because they
yeah,
just stay in one place. Right. Right. But did you notice the connection between that Fourier series app and the drawbars of the Hammond? It's essentially the same thing. Yeah. So the drawbars are literally the harmonics, the multiples 2 up to 8, and that's what you're controlling. When you bring the drawbars down, you're controlling these guys here, right? These dots. These are literally drawbars. But if I'd said that, no one else would have got the reference. But yes. Yeah. They're just the components of the Fourier series. So, okay. All right. Good. Well, enjoy reading. Yeah. Drop me a line if you've got any more questions. So, yeah. All right.
Thank you for the talk. That was
Sure.
amazing.
Thanks.
I didn't know about this thing. You can just spin it. It makes a sound.
Yeah, it's fun, right?
And I really like that app where it shows you like the different harmonics and the different
Yeah,
colors.
yeah.
What's it called?
So this is called a spectrogram. But I wrote this. I wrote. This one. This one is acceptable. Now I can do this. This one is okay. It has a sensitivity, and it goes from basically 0 to 6 kilohertz. So A, E, I, O, U. Right. So you get to see all of you can see formants. It's not perfect, but it's a good start. There's some other ones I think there's ones for the iPhone.
Okay.
I know there are. I've seen people play with them, but I don't have an iPhone. So.
I'm just gonna write that down.
Yeah. But I actually wrote this one, this GL Spect one I wrote in C myself, and that's why it's a little finicky. So there was a moment where it didn't work, and I was like, oh shit, I'm gonna have to reboot. Because there's some sound, it's using different sound.
But you see it really clearly, the different, with the human voice, there's sort of a spread, but when you're playing
now it doesn't work.
It's like straight lines with different colors. That's really cool.
Oh, right. It's basically it's a how do I put it? Let's go faster. Right, it's a piano player roll.
Yeah.
I didn't really say that. I should have said it. Right, but it's just really fun to watch the. I could have ran out of time, but to watch the notes. And then if you do. You see, but that sounds dissonant because a lot of these pure tones are coming very close together, as opposed to Yeah, actually you get nonlinear effects here where some lines appear that shouldn't be there. Not in the union of these two sets because of some nonlinear interactions. And then so there you can, because these two have a irrational ratio, basically you get lots of the lines are sort of coming close, but then that's what causes dissonance. So yeah, it's really fun just to like take a piece of music and watch it through this thing.